All right, sorry, I'll just finish writing this and then I'll turn around. Okay, thanks very much for the invitation to speak here. It's really a pleasure to be here. It's maybe kind of a slightly different crowd from who I usually see at conferences, so it makes it extra exciting to be here. So thanks very much for having me. I wanted to talk about joint work with Henri Darmon, both past and present, about an attempt to define singular moduli for real quadratic fields, to investigate them, first of all, numerically, and to find some conjectures about their structural behavior, and then to try and attempt to prove those behaviors explicitly. So what I want to talk about today has a lot to do with the work of Gros and Zagier, and this is where I would like to begin. So Gros and Zagier, in 1985, at least that's when the paper appeared, studied the following quantities. They studied the factorizations of the quantity which you obtain by taking the j function, evaluating it at a Cm point tau 1, subtracting the value of the j function at a second Cm point tau 2, both of which have quadratic forms with fundamental discriminant and coprime, let's say. These are both algebraic numbers, so there are differences as well. And I may take the norm all the way down to q to obtain an integer, an honest integer. Algebraic integers in general, I take their norm to q, I get an honest integer. Now, they studied this factorization, of course, in the beginning. What was the beginning of a very long celebrated story on Hausdorff points and what is still today one of the best bits of knowledge we have on the Bertrand conjecture. I would like to sort of highlight one aspect or one particular proof of their factorization formula. It gives two independent proofs, which will be of importance for the story to follow. So the story goes as follows. So the first Cm point tau 1 defines for me an imaginary quadratic field, which I'll call K1. Tau 2 defines an imaginary quadratic field, which I'll call K2. Both are quadratic extensions of Q, and define for me a biquadratic extension L, which has also a third intermediate quadratic extension of Q, which is real quadratic F. So F is going to be Q square root of the product of the two discriminants. Sorry for writing so small. It's a real quadratic field inside of that. L over F is cut out by some genus character, which I'll call chi. And what Gros and Zagier do is they study, or they look at a family which was defined by Hecker in the 20s, the 1920s. And it's a real analytic family. What they call ES, it's a family of Eisenstein series associated to this genus character. It has two variables, it's a Hilbert-Eisenstein series, of parallel weight 1, and it's modular for the whole group SL2OF, the full Hilbert modular group. It is not a holomorphic modular form, but rather a real analytic modular form that depends, so it's a family really, on a parameter S. And when S is equal to 0, the limit of this family defines for you a holomorphic modular form of parallel weight 1, 1. Unfortunately, this holomorphic modular form is equal to 0. This was kind of the starting point of their analysis. So when S is equal to 0, we have the specialization E0 actually vanishes, and the specialization E0 is also associated to the Galois representation, which you get by inducing up in the Galois group of L to F the trivial character, which is in this case just the trivial character plus this genus character chi. So the Fourier coefficients of this form, which is 0, are completely explicit. First of all, they're 0. They're also given by a character sum which you can show is 0. So it's in fact very established it is 0. This all sounds very trivial, but Hecker famously thought it was non-zero, so he made a sign error in his calculation. This is called Hecke's sign error. I won't write this down because it's a bit cruel to remember Hecke for a sign error. I always thought. But it's a famous instance somehow. Now, for Gross and Zagier, this was very good news because this meant that if they looked at this family, it has a vanishing specialization. Now the first order derivative itself retains the modularity properties of this family. So Gross and Zagier, so they compute the Fourier expansion of the modular form that you obtain by taking this family, restricting it to the diagonal. So now we have a one-parameter family of one variable modular forms of weight 2. It's still 0 after I restricted the diagonal if I put s is equal to 0. But I take the first order derivative, TdS, and I specialize this at s is equal to 0. What I obtain now is an analytic modular form of weight 2 and full level SL2Z. It's still analytic, and we prefer, of course, something holomorphic. So what they do is they compute Sturm's holomorphic projection of this whole form, and then I can remove this analytic part. Okay. A lot of work to do all of these steps explicitly. And in the end, what comes out? Well, 0 again, right? Because this space here only contains the 0 form. There's nothing else inside of it. So this thing here, so they find that the first Fourier coefficient, A1, first they calculate it completely. And they find that it's equal to essentially two contributions. The first is the logarithm of the norm of the difference of two J invariants. Which CM points you take doesn't really matter because we take the norm. And so the character here seems to know everything about this. And then they get a second contribution, and that second contribution is a sum, which I won't write down explicitly now because it doesn't really matter too much for our purposes, but it's a sum that ranges over finite primes. And it's a sum that's, the terms are 0 for all but finitely many q. And they're always multiples of log q. And the multiplicity is something explicit, which I won't write down now. This explicit thing, like I said, is 0 for all but finitely many q. A good explicit character sum that they find here. On the other hand, like we said, we constructed 0. This is also equal to 0 because this space only contains the 0 form. So if this quantity is equal to 0, you just bring this to the other side, you exponentiate, and you get the explicit formula for this integer. And factorization is completely determined here. The primes q that arise with this multiplicity in the factorization. So that's sort of the structure of their proof globally. Now, there's other proofs given in this first paper of Gross. There's one other proof given in the first paper of Gross and Zagier, which is an algebraic proof that uses elliptic curves with complex multiplication. Now, one thing, I would just like to make maybe two comments about this proof. The first thing is that this proof does not use any theory of complex multiplication. So the fact that these were algebraic integers had no relevance really to this whole proof. We never had to know that, and we could still carry out this proof. And you'll say, okay, the norm is there, so that seems to presuppose it's an algebraic number, but it's not really necessary because the norm is also the product over all of the taus with a fixed discriminant, is a finite product. And if you write it in that way, you've now completely eliminated all CM theory from this picture. The second point to make is that, of course, as we all know, the work of Gross and Zagier is about the computation of height pairings of Heegner divisors. And it's no different for this. What is true is that this whole quantity here is also an expression for the height pairing of the Heegner divisor on the Jacobian associated to the first discriminant with the Heegner divisor on the Jacobian associated to the second discriminant. So this is the Néron height pairing on the Jacobian. And of course the Jacobian of x of 1, which is a genus 0 curve, so this Jacobian is trivial, so therefore the height pairing is also trivial. So this is of course how the results that follow, so in the next paper of Gross and Sakier, as well as the work of Gross, Kohn, and Sakier, this is precisely what is being computed using kind of similar techniques. But what is interesting about this proof appearing in the first paper is that you never really have to know about height pairings to follow it. And this is precisely the situation that we will be in the real quadratic case. And so we will kind of make hay of this fact. So these are two observations on this proof, this analytic proof of this factorization formula that I want you to keep in mind for the remainder of the talk. All right, so let me now mention what we can say about these kinds of invariants in the case where tau 1 and tau 2 are not CM points but Rn points. In other words, where we replace the discriminants delta 1 and delta 2, not with not negative discriminants as they were in this story, with positive discriminants. And of course, already this notion of the J invariant evaluated at them doesn't make any obvious sense, even though there have been many interesting invariants also associated to them in the Archimedean sense. Algebraic numbers have often remained kind of elusive. So what I'd like to do is I'd like to sketch a p-adic approach due to Henri Darmon and myself. And the starting point is always a pair of embeddings. So we will consider an alpha 1 and an alpha 2, which will be embeddings of O1 and O2. And O1 and O2 will be the maximal orders in real quadratic. Oops, I dropped some blue chalk, sorry about that. And it broke in half. But, such is life, unfortunately. I'm sorry. So this is. Oops, oh my god. I'm doing a very poor job out here. You probably can't even read this blue in the back. Oh, okay, so that seems to be fine.
This is red.
It's like red. Okay. Anyway, this is not Hagoromo, I think. This one would never do this, but this blue one, unfortunately, is a little bit stickier. Very sticky, actually. It's like an impressionist painting almost up here. Okay, so real quadratic maximal orders. What I want to do is I want to embed them inside of a quaternion algebra. And really the whole work it's more general, but it suffices to keep in mind. So what I want to do is I want to take a maximal order inside of a quaternion algebra, which is indefinite. But really in our first paper together, we were always in the case where this indefinite quaternion algebra was just M2Q. Yeah, so it's just matrices with rational entries. And R would be M2Z, let's say. Let's pick that maximum order. In general, you can take an indefinite one, but everything I'll say today is just going to be for the matrix algebra, but I write it in this way so you can imagine how the fully general story goes. So now we have a diagram that's very similar to what we had on the board before. We have a K1 and a K2, which are real quadratic this time. And they're both quadratic extensions of Q, and they span a real biquadratic field, which has a third intermediate real quadratic field that I've also called F sitting inside of it. Okay. Now, these two embeddings endow this quaternion algebra with much more structure, and in fact, they make the quaternion algebra in a very natural way into a one-dimensional L vector space. We have an L structure on V. L is the tensor product of K1 and K2, so if I tell you what a pure tensor does, you know what a general element does. And what I'll do is I'll take a pure tensor K1 tensor K2, and my definition of this action on V is just that I take the first embedding and I multiply on the left, and then I take the second embedding and I multiply on the right. This defines for me a very nice action on this quaternion algebra. And this action satisfies the very nice law that if I take the reduced norm pairing on this quaternion algebra, sorry, I see some people standing up in the back, so I'm just a little bit higher for your comfort. So what it does is it satisfies for all A in L the law that if I act first on the first coordinate in the reduced norm pairing on this quaternion algebra, then that's actually the same as if I act on the second coordinate, but I twist this coefficient by sigma, where sigma is the unique non-trivial field automorphism of L over F. So it satisfied this kind of sesquilinearity with respect to the reduced norm pairing. And this is very nice. It's kind of serendipitous because it tells us, and this is an easy kind of linear algebra lemma, that there exists, in fact, a refinement.
Presumably you mean alpha 2 of K2?
Yes, indeed. That is what I tried to write, but it didn't come out very nicely. This is a K2. Yes.
Okay.
This is a 2. Yes, thank you. Okay, so this reduced norm pairing, by the sesquilinearity of this L action, actually allows us to refine, so there's a unique F by linear pairing let's call it the same symbol but with the subscript F on the quaternion algebra B, which of course has an F structure, has an L structure even, to F, such that if you take the result of this refined pairing, which is an element of F, and I take its trace down to Q, then I just obtain the usual reduced norm pairing, or the determinant pairing, because we were working on the matrix. Okay, it's just a linear algebra. Which comes down to the non-degeneracy of the trace pairing, as you can imagine. Not a very difficult thing. We'll use this pairing to rephrase, in fact, the construction that Henri and I made a couple of years ago, which was entirely in the framework of rigid meromorphic cocycles. Today, I don't want to mention at all what a rigid meromorphic cocycle is. And I'll just use the benefit of hindsight to define for you the invariance that we defined using this pairing. In kind of a slightly simpler way, perhaps, but one that is maybe equally mysterious in some other way. So in our first paper, we do the following. So we're going to make an analytic construction, but it's not going to be an Archimedean construction. It's going to be a p-adic analytic construction. So we begin by choosing our prime p. So we will choose a prime p, and I'll choose it so that it's inert in both K1 and K2. In the same way that infinity was inert in K1 and K2 in the work of Grosnes. Inert in both K1 and K2. Okay. In addition, if you picked a more general indefinite quaternion algebra, the prime p should also be non-ramified for that quaternion algebra. But with the matrix algebra, so I shouldn't write that down. Okay, so now what I want to do is I want to define a quantity which I'll call theta p times alpha 1, alpha 2. It's a p-adic number, depends on the datum of these two embeddings, alpha 1 and alpha 2, as well as the prime p that I chose. The star is meant to evoke that it's a multiplicative invariant. And what it is the following. So I'm going to take the product over all elements B in my maximal order, where I quotient out on the right by O2 star and O1 star on the left, of course viewed inside of R through these embeddings. And I will fix also the value of the determinant of these matrices. And it needs to be p to the power n factorial. The n hasn't appeared yet on the left-hand side, and that's because I'm going to take a limit as n goes to infinity to get rid of this n dependence.
Excuse me, can you try it?
To write a little bit bigger, absolutely. Absolutely. Yes. And please ask me again if I forget. Because that could happen. Oh, it's big. Too big. So B is going to range over the elements of the maximal order, modulo the maximal orders, or at least the units inside of there in the O1 and O2. And the determinant of this matrix B, or the element of the quaternion algebra if you had a different one from the split case, is going to be a fixed power of p, which is p to the n factorial. And the n dependence will disappear after I take the limit as n goes to infinity. And what I do is I take precisely just the values of this refined pairing, b comma b, f, But this would make absolutely no sense without the magic ingredient. And the magic ingredient is that I want to raise these guys to the power sine of b. And I have to tell you what sine of b is. Sine of b sine of b is an element of this set, so it's 0, 1, or minus 1, and it is the topological intersection of the oriented geodesics associated to the embedding alpha 1 and the embedding where I conjugate alpha 2 by this element b. So alpha 1 and alpha 2 are fixed. Now, what does this mean? Alpha 1 embedded in my quadratic algebra, it's M2Q, yeah, so this sits inside of M2R. I have a nice action on the upper half plane. And the two fixed points of this alpha 1, because alpha 1 is real quadratic, lie on the real axis. And so inside, so this is inside of H, which is the usual upper half plane.
Put the border, please.
Yes, and in fact, maybe, can I? Like this? You remember that we had to choose a prime, like so?
Or just keep writing on the next.
I'll go here, maybe with this as a compromise. Okay, so this is my picture of the upper half plane. The fixed points of alpha 1 are both real, so they lie just outside the upper half plane, but there's a hyperbolic geodesic that connects both of them, and in fact, you can distinguish between these roots. One is a stable fixed point, one is the unstable fixed point, so this comes with a natural orientation. So alpha 1 defines a geodesic in the upper half plane. Alpha 2 does the same thing, but I'm going to conjugate first by this element b to obtain a geodesic, like this, maybe, which is a geodesic associated to the conjugation of alpha 2, likewise taking the two real fixed points of that conjugate embedding, which comes with a natural orientation. Maybe it looks like this, and then I just take the topological intersection of these two geodesics. If they don't intersect, I get 0, which will happen most of the time. If they do intersect, I get plus or minus 1. Of course, I have to fix some orientation, and I'm right-handed, so a right-handed orientation. Henri is left-handed, so we have to left-handed orientation. But in the end, we end up with the same definition, just one over the other. It's not such a big drama. Okay.
Do you need that factorial to get the limit to converge?
Yeah, so indeed, so you already make a very good point. You can get away with slightly less than factorial. Yeah. But to be safe, we put factorial. And another point that you made is that secretly, of course, the statement is that this converges, yeah, which is not obvious already. And so you see, if you take this without this limit, this is still an infinite product if I didn't put this exponent. But this exponent makes it a finite product. This exponent will vanish for all but finitely many, but in the limit, of course, I get infinitely many contributions. So I get an infinite product of elements of F, which is therefore allowed to converge to something that is not inside of F. And so what we did, this was not the definition that we worked with. You will not find this in our first paper, but we had a different definition based on rigid meromorphic cocycles. What we did is we made lots of observations about this, numerical observations. So we observed a lot of structure lives on these quantities, and in fact they behave exactly as you would like the differences of singular moduli to behave. So we observed, we have hundreds of pages of evidence for this, which made us even more certain that it's correct than if we had a proof of it. But we would still like to have a proof of it, and that's kind of what I wanted to talk about today. So we observed that these are algebraic. But not all the time. They're algebraic without further making any modifications, only when p is 2, 3, 5, 7, or 13. If p is a different prime, they're not algebraic. We can still fiddle around a bit and make them algebraic by introducing maybe some Hecke operators. But they're only algebraic when p is one of these primes. And we'll get back to why that is later. When they are algebraic, we also looked at where they lie. They lie in the compositum of the two narrow Hilbert class fields, as you might imagine by analogy with j tau 1 minus j tau 2. And we studied their factorizations. And we observed that their factorizations are exactly the analog of the factorizations that you get in Grothendieck when you formally switch infinity and p. So they make a statement where this explicit number, which is still maybe on the board there, is in front of the log q. It's an explicit character sum, as I've mentioned, but you can also phrase it in terms of counting the number of embeddings in a definite quaternion algebra, or maximal order in a definite quaternion algebra, ramified at infinity and q. If you replace the infinity with a p, and you check, then in all of our experiments, these factorizations came out to be exactly the same. All right, so these were kind of the mysteries that we seem to have found kind of the right type of invariant, but it's a bit of a crazy construction, so it requires to be further explained, and also this constraint is a little bit, yeah, you would not like that, yes?
In our case, this thing, the thing you're writing more or less was the Green's function, which is defined for two analytic points. They don't have to be arithmetic. So my question is here, if alpha 1 and alpha 2 are just real points on the line, you still have the geodesics, and you let V do the same thing, does this still convert to some kind of a p-adic?
It's a very interesting question. It would be fantastic to do that, but I've never been able to make sense of this by the pure kind of silly fact that alpha 1 and alpha 2 being anything other than a real quadratic irrationality, all the structures disappear.
No, if you just take two geodesics with real endpoints, then for each fixed end, you'll still have only finitely many b that contribute.
Yes, but I don't know what this pairing is, this F
You
pairing.
don't know. You can't make sense.
So somehow the underlying structure evaporates. That doesn't mean it shouldn't be there, right? I agree with you, but I've never been able to...
So anyway, the answer is you don't have anything like a p-adic Green's function.
No. But in fact, I hope to convince you that maybe we should. In the second half of my talk, you're already convinced.
Okay.
Okay. So what I want to do now is I want to mimic as much as possible the structure of this proof to try and explain a little bit what the nature of these things should be. And we've already seen a sneak preview just now that it should be a multiplicative version of a Green's function. It arises from these cocycles, these rigid meromorphic cocycles, which feel very similar to kind of Green's cocycle, if you will. They live in H1, not in H0. So there are some differences, but I want to sharpen a little bit what the meaning of these objects is, and I want to also maybe explain why this condition was. You might object to, okay, I don't want any restriction on the primes. Then again, of course, in Grothendieck, P was always infinity, so there was only one choice. But these are 5 choices. But nonetheless, you know, it seems a little bit bizarre, so I want to kind of maybe try and explain a little bit why this condition is there. All right, so what I want to do is I want to explain all these things by giving you another definition, which is maybe even crazier than this one. But here we go. So p-adic high pairings of geodesics. All right, so I want to kind of put this in a framework where this acquires the interpretation of the analytic contribution at P to a sort of p-adic height pairing, which is a bit speculative, but its speculative nature does not stand in the way of us proving theorems about it. And so what I want to do is I want to take precisely this framework where everything was fixed, our invariant is fixed to, associated to a fixed pair of embeddings in a fixed quaternion algebra, but I want to now allow myself to consider also all the analogous setups, and that's very important in the proof, of all the other quaternion algebras together with such embeddings. And so I'll give a name to these sets, which is a name well, maybe not a very good name, I might change this, but I'll just call it quat-OL. And what it is it consists exactly of all of the possible situations like before that you can imagine. So when alpha I is an embedding of OI inside of R, and I take the set of all of these. And of course, if I take such a pair of embeddings and I conjugate by norm 1 unit, I don't consider these different. So I take them up to simultaneous conjugation by elements in R1 star. Now this is the kind of the integral version. I also want to take a non-integral version because after all this structure here, it didn't really use the integral structure, this the pairing that we have there. So I can also define what I'll call a quat L. And quat L is precisely the same thing, but where I don't insist that these come from embeddings of the maximal order in some fixed maximal order of the quaternion algebra, but rather just an indefinite quaternion algebra together with such a pair of embeddings, and again up to simultaneous conjugation. And if I have such a thing, that's of course a stronger structural thing, so I have a map that goes from the integral version to the non-integral version. And even if I had some non-integral guy, there could be several ways to sort of fit a maximal order around the image of the embeddings on the maximal order. So this is kind of how the two relate. Now, for each, this is kind of again, a very silly sort of linear algebra calculation fact, but significant for us. So for each element that I take inside of this quat L, well, you see, I just explained to you how to associate such a refined f bilinear pairing to this data. And if I take this f bilinear pairing and I take the value at 1 and 1, that defines for me an element of f whose trace is the reduced norm pairing of 1, which is 1. Yeah? So it defines for me a canonical kind of trace 1 element of f. Okay. So for each element, we have a well-defined, because it doesn't depend on the pair of embeddings up to conjugation. Here, the conjugation leaves that invariant. And this invariant is the pairing, this magical refined pairing, evaluated at 1. So this is an element of f, and it has trace equal to 1. Now, you might think that you lose a lot of information by only remembering this number, other than this data, which is a lot of data somehow. You have two embeddings inside of a quaternion algebra, etc. Here I just have one element of a field, and that field is always the same. It doesn't depend on the quaternion algebra. Nonetheless, here's a lemma. I'll put Jacquet, but I promise you won't find it in Jacquet. It's very implicit somehow, but he does all the hard calculations to verify that in fact, if I take this map from all of these quaternion embeddings, by taking this refined pairing evaluated at 1, I obtain an element of f, and its trace is equal to 1. And this map is a bijection. Meaning, you can recover completely from just this element, both the quaternion algebra and the pair of embeddings up to simultaneous conjugation from it. So it's quite powerful. I just have to remember this number, and I remember all of these quaternion algebras at the same time. And of course, if I take different elements of f, I might end up with very different quaternion algebras, but that doesn't really matter. We also have the ones that come from an actual integral structure, and as you can imagine, if you lie in the image of this, then secretly there will also be some integrality of this invariant, and there is. This element will also always lie in the inverse different, and of course it will still have trace 1. Okay, so this invariant has also this integrality property. Okay. How am I doing on time? Oh, there's a clock. 30. Okay, so I'm about halfway.
So what does the dotted line mean? That it doesn't exist, or it,
Sorry?
what does dotted mean? That it doesn't exist, or just
Delta.
Dotted.
The little dots. Oh, sorry, no, it just the induced map, I guess, or rather. Yeah, I just mean, yeah, this maybe is kind of a sad notation, but I just mean that the invariant lands inside of the inverse difference. So if I follow this map, then actually I land inside of it. So I factor through this inclusion. All right, so why do I do this? It was bad enough defining an invariant for a fixed quaternion algebra. Why do I want to consider the ensemble of all of the quaternion algebras and all of their embeddings, maybe I'll leave this as I don't hope that I'll get everything on the left board, but you never know. So, all right, so what I want to do again, just like in the previous section, I want to fix some data. I want to fix, well, first of all, I want to fix a prime P, just like before, because you'll notice that everything here was just still global. Now I want to do some local construction. I want to take my prime P to be inert in K1 and K2. I want to also fix, I guess, an embedding of Q bar inside of QP bar. So I know what it means for a p-adic number to be algebraic. And I also want to fix kind of what you might see as a base point. And this is necessary to anchor all of the definitions in a crucial way. And the base point will be an initial piece of datum of this form. Yeah? So for us, for the construction, you could do it in general, but I promised that our base point was always going to be an embedding inside of the maximal order M2Z inside of the quaternion algebra M2Q. And I have this pair of embeddings alpha 1 and alpha 2. And so this will be my fixed base point in these quaternionic embeddings, integrally speaking. So of course, to this fixed base point, there is associated this invariant, right? So we have this analytic invariant already. But what I'll do is I'll associate yet another one to it that has this as one of its components. Okay. Now, I need a couple of quick definitions. This is a bit ad hoc. The construction is a bit nicer than this, but I want to do it in this kind of more ad hoc way, so I can give you at least a definition. Suppose I have now some other guy, which is not necessarily the base point, inside of this set of quaternion embeddings. I don't want to give names to the embeddings because I don't need them, but they exist and they give all the structures I need on R, which is nearby to R0. So what I'll call P nearby. This means that its ramification set differs from that of our base point in only two places, and one of these places is P. So think of, in the work of Gross and Zagier, you start with the quaternion algebra, which is M2Q again, and you pick all of the definite quaternion algebras that are also ramified at a finite prime Q. So the B infinity Q's appear there. Here for us it's the same, but infinity is P. So P nearby, so i.e. the ramification set differs from the ramification set of R0, which is trivial in this case, but in general it will not be, only in two primes and one of them is P. So it's P times P. Alright, so now what happens? What happens is the following. So I have to define some algebraic numbers for you, which will appear in this story. Because we don't have singular moduli to begin with, so we have to somehow introduce some algebraic numbers to this picture. And I'll tell you where these algebraic numbers lie. So we have the extension L of f, which is the extension of the biquadratic field over this real quadratic field that was intermediate inside of L to K1 and K2. So I have this quadratic extension. And I have also its narrow Hilbert class field, which I'll call HL. So this Galois group here is the narrow class group of L. And inside of there is the compositum of the two narrow Hilbert class fields of K1 and K2. It sits as an intermediate extension inside of this narrow Hilbert class. That's kind of the picture that you get, where H1 is the narrow Hilbert class field of K1, and H2 is the narrow Hilbert class field of K2. It's inside of there. That's because this thing is not ramified anywhere except at infinity, so it must lie inside of there. Class field theory tells you that this is indeed an intermediate extension, and so we get a surjection from this Galois group onto this guy. Okay. Now what happens? Roughly speaking, there exists, and I want to say unique, it's not really true, but I'll say it anyway, and then I'll say why it's almost correct. There is a unique prime, German Q, dividing Roman Q, inside of H1, H2, such that if I take this R0, my initial base point is M2Z, it's also endowed with the structure of a projective OL module of rank 1. It's an invertible ideal inside of L, by this L structure that I've put on it. And it need not be trivial, right? It could be some non-trivial class. That class I'll call R. I'll take this one first. And then I'll multiply it by the inverse of the class of R0. So now I have an element of the class group, narrow class group of L. So I sit here, and I view its projection inside of H1, H2 over L. That should be equal to the Frobenius element over P times the Frobenius element of this prime Q that we're looking for. Now this Frobenius element of P, there's a distinguished P already by our choice of embeddings. So we already know canonical prime above P. What I'm saying is that I can multiply the Frobenius of that guy with the Frobenius of some prime above Q, so that the product of the two is precisely this class in H1, H2 over L. So this equality takes place in the Galois group of H1, H2 over F. Yeah. That's where this takes place. Now, the uniqueness is not quite true. It's true if, instead of this Roman Q, I put one of the two primes above Q inside of F. Yeah. That prime Q is necessarily, because it's inert in K1 and K2, it's necessarily split in F. And in fact, if I choose an element of this quaternion algebra, I didn't tell you that, but I've secretly already chosen a reflex prime above Q inside of that. So this data already picks a distinguished prime above Q inside of F. So if I had put that prime here, this would really be. But I didn't want to introduce notation, so I'll just tell you what that is. All right. So that's the first observation. There is a distinguished prime above Q associated to this datum of my choice here if I anchor it with a base point here. So this pair of quaternion algebras defines for me a canonical prime Q inside of H1, H2. And that's, of course, where we expect the algebraic invariance to lie, right? After all, the difference of singular moduli would have lied in that field. Okay, so now what do? We take this prime Q, this is the second fact. We take this prime Q, and I'm going to define a virtual unit for you. So there's a unique, what I'll call UQ, and UQ is going to be an element of H1, H2 that is a Q unit. And in fact, it's only a Q unit up to taking a power. So I'll be inside of this Q unit group tensor Q, a finite dimensional Q vector space. And I'm also going to insist that complex conjugation negates it multiplicatively, so it sends it to its inverse. So there's a unique element in there such that this element generates Q modulo the complex conjugate of Q. Not modulo, but divided by. Yeah. So this is a fractional ideal. I just have to raise it to its power until it becomes principal, but raising to that power comes for free because I'm working in this tensor product with Q. So it's a virtual unit. It's a unit tensor Q. That's what this UQ is. It's a gross Stark unit. Okay, so now, here's my definition. With this in the pocket, I will define for you, for every such R, a unit. So I take my base point, R0, and my other quaternion algebra, which might be a completely different quaternion algebra, maximal order inside of there, and I will define the unit to be one of two things in general. I will say that if it is true that these two quaternion algebras are P nearby, so if, in other words, R and R0 differ only in ramification of P and Q, then I will take precisely this UQ, but I'll take its norm down to QP. And of course, that sounds like a local thing, but there's a distinguished prime above P inside of this extension, so I just take the norm with respect to that distinguished Frobenius. So it's a global unit. Global unit, or global element, virtual unit inside of H1, H2. Otherwise, this is not the case, but then it's just one. So I don't want to consider those cases. P could also be equal to Q. This I allow. So it's empty, let's say, so that's the case where P is equal to Q. You could make the same kind of construction. All right.
So
Yes.
what does that tension by Q mean? I missed what you said. Like,
Yeah, so this is just, it's a group, it's a Z module, and I tensor it with Q over Z. So it's a,
okay,
so,
you're not extracting roots. It's still inside.
well, kind of, yeah. So the elements of this group have the property that there's always some finite power which I have to raise them to so that they become an actual Q unit. They're virtual units. So in particular, the logarithms of these guys are well defined.
Okay. Okay.
I can take well-defined logarithms of these, and I will do that in a second.
What logarithm? Is it a logarithm? It's some p-adic logarithm.
For us, it'll be a p-adic logarithm.
And there's no ambiguity. I mean,
There's no ambiguity there.
usual logarithms do have one.
Yeah, so we'll see. Yeah. Okay. So the height pairing. That I want to define for you. It's a symbol, I'll denote it like this, which is defined really almost through its local decomposition. Almost. So what it is it has two components. The first is the p-adic logarithm of theta p star alpha 1 alpha 2. So the bizarre invariant that Henri and I defined a couple of years ago. So I take its p-adic logarithm. That'll be one of my contributions. And then there will be a second contribution. And the second contribution will be a finite sum indexed by elements, which I'll call nu, of the inverse different that are totally positive. And I want these guys to have trace 1. Okay. Will be a sum over such elements. And for every such element, I can look at the map, which is it still on the board? Yes, there it is. I can look at this map, and I can take all of the quaternion algebras that have precisely that invariant nu. I'll take a second sum over all of the r's that arise in the inverse in the inverse image of this invariant map of nu. So those are all the quaternion embeddings, and it will be very different quaternion algebras appearing, which allows such an alpha 1 and an alpha 2 together with that alpha 1 and alpha 2, which I'm forgetting, that give rise to this invariant. Yes?
Sorry, I thought it was a bijection of that map there.
Yes, but
one pre-image.
it is non-integrally. But integrally, that's not true. So the top arrow
okay,
is a bijection.
Okay.
There could be various ways to fit the maximum order. Yeah.
So the top is a bijection.
The top is a bijection. Yeah, that's correct. Okay. So now this sum, it's a finite sum. I'm giving myself these quaternion algebras to this finite sum. And what I'll do is I will take this unit. So UQ. Sorry, did I call it UQ? No, I called it something else. I called it U. There it is. U of R0 R. I'll take its p-adic logarithm. Now, you have to choose a branch of a p-adic logarithm in general, but that doesn't really matter for us. You just have to pick the same one here and there. You can pick it essentially freely. It's often convenient to choose the Iwasawa branch, where the log of p is defined to be 0, but it's not really necessary. Okay, so this is a very bizarre definition. It doesn't look anything like a height pairing at all. So my job is a little bit to convince you that it is, which I'll do by writing down the main theorem of our work in progress. Okay, so here's the main theorem.
Why?
Yes.
Why this sum? Why do you write nu at all? It's just a sum over all r. I mean, every r has some invariant, which is always is traced once.
Yes, that's correct.
So why are you writing a double sum? It's just a sum over r.
Really positive?
There's no restriction on r. It's invariant to something.
Be totally positive.
There is no restriction on that. I mean, we're taking, yeah, I mean, I'm not sure what the question is, but there are restrictions on nu. So I'm not relying on
all nu, and all R whose invariant is nu.
It's totally
Yeah,
positive.
but nu has, it lives in a finite set. So I'm not taking all of the elements in F or anything. I want to impose conditions on nu. It has to be totally positive. It has to be inside of the inverse difference.
I can't see it.
Sorry, this is a bit
Also, it's
small.
finite. Okay, so you're summing over all nu such that the invariant is totally positive.
Totally positive and trace 1.
I thought it's always in trace 1.
Yes, indeed, but okay. Here we don't know that yet, but indeed.
No, but if it's
That's
the
correct.
invariant of an R, I thought the invariant
That's
was
correct,
also
yeah.
trace
But the
1.
total positivity is still
Yeah, I couldn't
yeah.
see the plus.
Yeah.
It's too small.
Okay.
No, then
And
it's
the
back
fact-
to another, yeah.
No, absolutely. And the fact that, yeah, it's integral gives us also this integral embeddings, which is important, of course, in our story. Indeed, yeah. So there are, it's not an unrestricted set. Okay, so here's the theorem. So the first is an attempt to make it look a little bit more like a height pairing. And I'll mention, even though I won't give a super precise definition of the multiplicity, because I didn't do it in the case of Grothendieck either. I'll tell you that we have a local decomposition which has the following shape. If I take this height pairing associated to alpha 1 and alpha 2, then, well, my definition said there was first this kind of infinite product, which is maybe more of an infinite sum by this logarithm of this invariant. And then what I can do is I can rearrange this sum by taking every time a UQ appears, counting how many times it appears coming from a quaternion embedding. So I can flip around this sum, rather than being a sum of quaternion algebras, being a sum over these Q units, and then counting the multiplicity. What I get then is I get a sum over primes, and these are primes, by the way, in H1, H2. Right? They're in this big extensions. It's like a height pairing over this huge extension because we didn't take a trace or a norm or anything like that. So these are indexed by primes inside of here. They will have the p-adic logarithm of these units. In fact, let me put the norm of UQ. Yeah, so I rearrange them according to the Q units. And now I want to make explicit which multiplicity arises here. And this multiplicity has a topological interpretation. I'll write it down first, and then I'll tell you roughly how this works. We started with our fixed pair of embeddings alpha 1 and alpha 2 inside of our base point. Now what happens is that besides the modular curve that we get by quotienting out the norm 1 units of the maximum order, which is x of 1, there's also all these other quaternion algebras floating around. And if I take likewise the quotient of h by the norm 1 units inside of this maximum order, I get a Shimura curve. And xpq is the Shimura curve I get from the nearby quaternion algebra ramified to p and q. So that's xpq. On xpq, I likewise have embeddings, and there's a distinguished alpha tilde and alpha 2 tilde, which I'm not telling you what they are, but there's a distinguished pair of embeddings that comes along with it, coming from the choice of alpha 1 and alpha 2, which define for me geodesics on the Shimura curve. So this Shimura curve, even though our initial modular curve was genus 0, I have some Shimura curve xpq for every q is fixed that I get as a quotient of the upper half line by the norm 1 units. And on there, I get from alpha 1 and alpha 2 a pair of geodesics, which may go something like this. And what I do is I just take their homology intersection product. It's a small line, there's an additional q weighting in this, but roughly speaking, in practice, it's almost always just the topological intersection product. When P is 2, it has a tendency to have the multiplicities kick in a big way, but it's good to think about it in this way. So we have an interpretation, completely explicit formula, which I'm not telling you now, for this multiplicity. So in other words, for the factorization of the number, algebraic number that we're trying to construct. Okay, so but it's a result because the definition is different. It's not by definition. Okay, so nice to know. It looks already a little bit more like the local decomposition of a height pairing. It has some analytic infinite contribution, and then has this finite contributions given by explicit intersection numbers as the multiplicities. So maybe that's not enough yet to convince you. It might seem very frivolous, but the following, hopefully, is a bit more definitive, is that in spite of not having a good geometric interpretation of this height pairing, it doesn't really matter. Because what we can show is the following modularity result. If I take this absolutely bizarre definition, and I make a generating series for it, by taking the p-adic height pairing of alpha 1 and then hitting it with a Hecker operator, Tn indexed by integers n, and I take n greater than or equal to 1, and I put that in a generating series with the value of Qn, and this object is modular. In fact, it's a cusp form of level gamma 0 of P. The P had to enter somewhere, of course. It was with our construction this whole time. Okay, so that's the result. So maybe I'll make a few comments about this, just right at the end. Exactly. Yes, that's the first comment I wanted to make. Why on earth did P have to be one of those primes in the beginning? Well, because those are exactly the primes for which this space contains just 0. And if this space contains just 0, then that means that this height pairing is 0. In particular, the first coefficient, which is the height pairing of alpha 1 and alpha 2, must be 0. Therefore, this thing must be 0. So I just bring this to the other side of exponential, and out comes the result. So you get kind of you get an algebraicity result out of this as well as a factorization result without ever knowing what the geometric meaning of this height pairing really is. Because they're geodesics, they're not algebraic cycles, so it doesn't a priori make too much sense. So that's the first comment that I wanted to make. The second comment is, how do you prove such a result? You make a very bizarre definition, you have to prove this modularity result. Now this is very difficult, but it mirrors very much what happened right at the beginning of this talk. So right at the beginning of this talk, we started with the work of Gross and Zagier, and we saw that we had this real analytic family of Eisenstein series, which vanished in the specialization, and then we restricted it to the diagonal. That was the first operation. We took the first order derivative, second operation, and then we took the holomorphic projection. I say we, but they did. So these are the three operations that we wanted to subject our family to. Now, remember, from the beginning there, I mean, it's an Eisenstein family, so we're doing something Archimedean. So it's important that we stay inside of the continuous spectrum of the Laplacian to have such deformations available. P-adically, things are a bit more comfortable. So we don't need to be in this continuous spectrum. Everything is in the continuous spectrum. So p-adically, things are much more deformable. And that's exactly what is happening here, is that this series, this whole series really, arises in our proof as follows. So what we do is we take a family of Hilbert theta series indexed by some parameter s, which is now a p-adic parameter. So it's a p-adic family. And it has two variables. It's a Hilbert modular form on f. So maybe I should have kept the diagram somewhere on the board. Like so. So it's a family of Hilbert modular forms, a Hida family, in fact, on f. So it has two variables. And what it is it's a cusp form. In the specialization at s is equal to 0, it's of weight 1, 1, but in general it's of weight 1 plus s, 1. So it's partial weight 1. One of the weights stays 1, the other one varies p-adically along such a line, which is essentially uniquely determined. The eigenvariety which prescribes how these families behave is a tau over weight space there, for those of you who know that. So this thing, it's a Hilbert modular form, also on the full group SL2OF, the Taine group, and there's a p-adic level implicit. And it's p-adic. So what we'll do is we'll restrict it to the diagonal. We take the first order derivative of this series at s is equal to 0. And then we end up with the analog of what we had before, something of weight 2. And it was analytic before, but in our case, that's replaced by overconvergence. It's an overconvergent modular form of Taine level 1. It's overconvergent, so what we'll do is we now take the analog of the holomorphic projection, which is the ordinary projection. And the ordinary projection, that's the limit. This is defined to be the limit as n goes to infinity of up to the n factorial. That's where that limit came from, in the definition that I gave earlier. If I do all of these things, I land inside of a space of ordinary forms of weight 2, which by result of Coleman is always classical. So you always land inside of the space S2 gamma 0. This is roughly the structure of the proof. The crucial difference is that we have to work pretty hard to find the Fourier expansion of this. And that's because if you're not an Eisenstein family, there's no explicit description of the Fourier expansion at all, especially in this highly non-orthodox weight direction. So what we have to do is, it's a family of cusp forms, and to make explicit its Fourier expansion, we have to compute the deformations, the p-adic deformations of the associated Galois representation. And the Galois representation will be, this will be a finite sum of things that are induced from L to F by certain characters of the class group, which need not be the trivial character. In fact, we have to do all the characters, all the non-trivial characters, and we'll take certain weights. So that's just to give you an idea of the structure of the proof. You have to work harder for the Fourier expansion to get it, or know what the Fourier expansion is in the first place, but then all the other steps are highly analogous to what happened with Gaussian. In fact, almost exactly the same. Diagonal restriction, first order derivative in ordinary projection, and an explicit computation. Of course, this projection operator has a very different nature, but nonetheless, there's a very nice kind of philosophical accordance between the two proofs, and I would argue this is really the same kind of proof, where we've used, of course, the fact that that proof in Gross and Zagier did not use CM theory. Very important for us because we don't have RM theory. There's no RM elliptic curves. So to circumvent that, we do that proof of inspiration. And the second is that it's secretly computing, of course, a height pairing between two Hegler divisors, but we didn't really need to know that for the proof. There was no geometric input necessary for that proof. And both of these facts are perfect for our purposes because we're exactly in a situation where we don't have either of those things. Okay, so with that said, I think my time is up, so thank you very much. Thank you.
Thank you for this very nice talk. So, questions, remarks?
So, well, of course, it's an incredible story, but that goes without saying. In the first part, you give a formula for the decomposition into prime. Yes. You have a product of prime ideals, and therefore you have an ideal. In our situation, we knew that that ideal was principal because we already had complex multiplication theories, the difference of the case. It's already an algebraic number. It generated some ideal, and it was that ideal. In your situation, you have the ideal, but do you know that you have an algebraic number?
Yeah, I mean, these UQs, you see, this is kind of sneaky. We defined it to be a generator, but I've insisted here that I'm in the -1 path for complex conjugation. So this kills all the global units. Yeah, so this global unit ambiguity goes away
so you
by virtue of
well-defined algebraic number.
Exactly. And that's the whole reason that the p-adic story and kind of gross star conjecture works, because these units can be cut out exactly without unit ambiguity by this condition. And that's very important indeed. So that's a good
Oh, I see. So that the Q of a Q bar is very important.
Exactly. It's very important. Otherwise, you wouldn't be able to cut out these units. Yeah. And that's an additional advantage that the p-adic star conjectures, for instance, also make use of this fact, have over the Archimedean ones. Your ability to produce a kind of a canonical unit, that should be the right answer.
It probably answers a bit of the other question I had in mind. I mean, there are only a handful of P's for gamma 0 P as genus.
Yes.
Yeah, not that you need it, you can use Heck operators, as you said.
Right.
But there are many more P's going up to 71 where gamma 0 is star of P.
Yes,
It's
indeed.
genus 0. You can't use those because it's the wrong complex conjugation.
Well, we do use those. And so what you do there is, yeah, you have to, you take a,
No, here it's only gamma 0 P that has to be genus 0.
yeah, so
P is
you're completely
71.
correct. But what you could do, and this is also what we do in the paper, I mean, it's kind of the same as using a Heck operator. We just use Atkin-Lehner at P. And we force the invariant to be in the plus part. So we take kind of a Hecker projection to force it into the plus part, which feels a bit more innocent than another Hecker operator. And then we produce also algebraic invariants for all of the monstrous primes. So all the primes dividing the order of the monster group give rise to algebraic numbers precisely in the way that we said. Yeah. Yeah. And the proof of it would also follow here, but would be a slightly weaker result because you'd have to also take here the product of this guy together with alpha 1 and then alpha 2, where the fixed point is multiplied by P. So it's this multiplication by P, it's like an Atkin-Lehner at P action, which also forces these things. And then you can show that it lands inside of, normalize with this, also with the Atkin-Beta review, and then you'd still have a zero space. Yeah, it's a good observation.
Marta. So in 2 you can write this modular form as the sum of linear combination of eigenforms.
This thing.
Is there a meaning of the coefficients next to the eigenforms again?
It's an excellent question. Not a priori. We would love to have this. And so the expectation is that it should be the case that if you project onto an F, let's say it comes from an elliptic curve, that what you get there is you should get a height pairing of the associated Stark-Hagener points on this elliptic curve. That's what it should be. Unfortunately, we don't know that Stark-Hagener points are global. So there's not even an a priori justification for what this height pairing really should be. But that's what it should be. And it should be the height pairing of an individual pair of Stark-Hagener divisors, meaning you don't take the average over the class group. So you get a rational point that's not defined over Q or anything like that, but over H1, H2. You get it for every such pair. That's the expectation. That would be great if we could prove that. But currently that's not within reach. Excellent question.
Yeah, I was just wondering, I mean, when you, at the very top, when you define this theta thing.
Yes.
It seems that there is a further information, which is the point of intersection, when it does exist.
Yeah.
What happens to it? I mean, is it related to the BBF, or is it, can you use that to define this for general geodesics?
I don't know. Yeah, I honestly don't know if the intersection point plays a big role. And in fact, I mean, of course, it's kind of a small distance invariant, so it's hard not to find a relation with any of the definitions we made there.
No, but I mean,
but
to follow with Don's suggestion,
absolutely.
I mean, it could make it a purely geometric thing without fields.
Maybe, but it feels to me that the intersection point has maybe less of a role to play. Never say never, of course, because really all that matters, and you also see this p-adically, is that it's just the combinatorics of the 4 points at the end. So the cross ratio really of these 4 points.
Well, they also know the intersection.
Right? They know the intersection, but they don't know the sign of intersection necessarily. So it's a slightly finer thing than that. But my feeling is that, well, I don't know if it miraculously solves any problems. It's also in the wrong kind of number field.
Where is it?
It's not real, so. No. L is real, so it's a bit of a mystery. Yeah.
So, other questions?
Yeah.
Maybe this is a very naive thing, maybe there's nothing to it, but in this real case, the fields related to K1, K2, and F are all symmetric with each other. Right?
Yeah.
It's like in an imaginary case, somehow there's a distinguished real field.
Yeah.
Is there anything there that you have this extra symmetry that you could take F and K1 and then do K2?
Absolutely. Oh, sorry. Which symmetry? You're swapping K1 and K2? Or?
No, no.
Like taking F into K1.
Yes. Well, that's a very annoying question. So, yeah, there is, so swapping K1 and K2, that's completely correct. There is that symmetry. In fact, it's an anti-symmetry for us because of that sign of intersection. So if you swap alpha 1 and alpha 2, you get for the invariant theta 1 over the other invariant. So that is something that I want to show. But yeah, swapping these fields, it's very annoying. I mean, all the algebra really takes at various places advantage of the fact that these have co-prime discriminants, etc.
Oh, it's not symmetric.
So if you swap F and K2 and try and construct a Hilbert modular from K, I don't know, you could do something, but it would be a lot messier for starters.
I didn't realize this really F is distinguished in that K1 and K2 have prime discriminant. And then F
No, not prime discriminant. Yeah, co-prime.
What did I say?
So
You said prime discriminant.
yeah,
co-prime.
So therefore, F has a discriminant which is visible by both of them.
Yeah, okay, so it's not so symmetric as I thought.
Of course, it's not super important that they are, but it's just we've made so much use of these simplifying assumptions that it'd be a little bit brave of me to just claim, yeah, it's the same. It's probably a lot more painful.
You don't need co-prime in the whole story, in the original story.
Yes, I mean, in fact, K1 equal to K2.
Which is not close to the symmetry.
Yes, yeah, no, absolutely. So in fact, what we did in earlier work also with Alice Pozzi is a degenerate case of this where K1 is Q cross Q. And K1 is Q cross Q, K2 is still some other field, F is K2. And so in that case, things are a lot simpler because the family that you start off with is really a family Weissenstein series. And so there you parallel really modulo, of course, the fact that we took completely the wrong setup. The proof mimics just very literally the proof of Grossman's. It's a family Weissenstein series, so there's not this additional step. But the invariants are a lot poorer in that case. So we still construct algebraic numbers, but they're Gross-Stark units. They're only p units. They don't have any interesting factorization. So they're more like the elliptic units, which are very nice because elliptic units, of course, they're very kind of rigidly obeying the L function, so they're very rigidly structured, but arithmetically they're also a lot poorer because they don't have all these rich prime factorizations of the singular moduli, which gave rise to all this progress on BSD, etc. So that setup was arithmetically much more limited somehow in that what we produce are just p units. And that's also reflected by the fact that the automorphic form, maybe the representation was also a little bit, it was split, yeah, so it was just a sum of characters. Whereas here it's an irreducible representation, so it's a bit rich, it allows for a richer factorization.
Yeah. So I already have 1.5 questions, but in Grosse here we normally did higher weight, but it was much easier. It was much, much harder to do weight 2, which is the one we cared about. Yeah. Do you have something here where you end up with cusp forms of weight 2K?
Yeah, so absolutely you could, but I haven't looked at it, and the reason is that I don't know how to define the invariants that should appear there.
So
and it should be done.
You don't know. You don't yet have such a thing.
Yeah, you could mimic this thing, of course, and do a similar story in higher weight, and all the steps would be roughly the same. The only thing is you wouldn't have another a priori interpretation for what this analytic attribution is. You could follow the form. You could follow the Hecke algebra, the form, do all these 3 operations to it, observe the expressions, and then just declare that this is. But we don't have the rigid normorphic cocycles as it stands. It's really a weight 2.
But can't you then run your proof backwards? That
Of
this
course.
equals that and see what that would have to be.
You certainly could, yeah. And in fact, I think Henri has a student who's doing exactly that. Yeah.
Yeah, I suggest we thank the speaker again.